All right, let's talk about differentials. Now, you've already seen differentials when we talked about the Leibniz notation for the derivative, right? So if you recall, in the change in y over the change in x, right, which is essentially average rate of change, right? It's slope. As x goes to 0, this goes to dy dx. That was the definition of the derivative, right? And so dy and dx just they're just represent a very small change in the quantity, right? So it's very small change in x produces a very small change in y. All right, so we've used differentials when we've used I should say as delta x goes to 0, right? That's the definition of derivative. Um, so we've seen differentials in the Leibniz notation. Now, we know that, here, I'll write it down here, delta y over delta x is approximately equal to f prime of x, right? F prime of x, that's dy dx, right? And so, we can actually rewrite this because this is just a fraction, right? Delta y over delta x is a fraction, so delta y, if we multiply both sides by delta x, we get f prime of x times delta x. All right, this is our linear approximation, and this is the point slope formula. That's what this is. It's just written a little differently. This is the point slope formula. Okay, so now there's a little technicality here with the differentials. So we say that a small change in y is approximated by this differential, that f prime of x times dx, right? The small change in x. But it looks a lot like this, right? It makes sense because we know that's true. And as x goes to 0, it's going to get closer and closer. That small change in y is just going to be the derivative times the small change in x. That's all a differential is. It's just that dy and that dx. All right? All right. So let's go ahead and take a look at example 5 here. So it says use the notation of differentials to write the approximate change dy given y equals f of x, which is cosine of x, given a small change dx. All right, so basically we're just going to say dy is equal to the derivative of cosine, right? F prime of x is equal to negative sine of x, right? Negative sine of x. So it's so f prime of x is negative sine of x times dx. Okay, so all we're doing is using the differential notation to write the the approximate change in y given a change in x dx. This small change in x is dx, the differential dx. So now if we use this, we can find a small change in y if we're given the change in x, right? So we're saying if x increases from pi over 6 to pi over 6 plus a little bit, 0.1, then what is the approximate change in y? So we'll use this differential, and we can then just use x as pi over 6. So we have negative sine of pi over 6 times our dx in this case, right? Our change is actually this. This is our dx. So I'm going to make this times 0.1, right? That should be a 6. That doesn't look very good. But here, I'll fix that. Fix that so it looks like pi over 6. I think you probably figured that out, but okay, pi over 6. All right, so what is sine of pi over 6? Let's just figure out, we'll just evaluate this, right? Now, pi over 6, right? If you think about the unit circle, right? This is where you have to know your know the unit circle. Pi over 6 is essentially 30 degrees, and sine is the y-coordinate, right? So I always just draw the triangle out. And so the the y-coordinate is sine. The y-coordinate is sine, so it looks like sine of pi over 6 is a half. But it's negative, so it's negative 1/2 times 0.1. And if I multiply that out, it's 0.5 times 0.01, so it's negative 0.05. So that would be our approximate increase in y when the angle changes by just 0.1. Okay, so there you go. We just used some differentials. I'll meet you in the next video and we'll talk about quadratic approximation.